All right, hi. Welcome everyone. Welcome back. Sorry for the delay. I was a bit late this morning coming in, and then my coffee took forever. And I do need my coffee to stream. So today we have last week. Oh, let me just adjust the camera here. Let's see how. Let me see if I can adjust the camera a little bit. Just really physically. Yep. All right. This is for really just. I really just came in, set up the camera, and started. And now, as I do it, I realize that it's a little bit off. Yeah, I think this is better. It's better. Anyway, so this week, despite the delay, I will do a full session, a full hour, more or less, and I will also, last week there was just a lot going on, nothing to do with extremely open science or anything to do with any of these, just other random things going on. And so there was not a lot of time. I was pretty tired. And so I also didn't do a recap. I'll do a combined recap this week, covering whatever we do today as well as the updates from last week. So with that, let's just see where we were. So where we are, and where we are, and so we were on the log branch, and so as I said, so this is because we had some code that was okay, but I didn't think it was good enough, so I'm gonna switch to the main branch. And see, yes, so there was this code, this navigate arrow, and I'm gonna so how should we do this? So it's in the log branch, and I want to get out. I will actually do this work. Yeah, okay, so I did this, so I'm now on the main branch, and I diffed. Let me just the camera. Camera a bit. Where's the? Sorry, I wanted the opposite of that. Yep. Maybe even a bit. Yeah. So I'm on the main branch. So if I say git diff log, this shows me the difference between this branch and the log branch, or I think in the direction, so going from the log branch to the main branch, and so I can use that to patch, and then so this is what I did, and then I want to reverse the patch because I want to go from main to log, and then P1 just is necessary because to drop this first I don't know what to call it, like this first element in the path. So because here this diff shows that on the one side there's the source navigate arrow, and on the other side there's nothing. Okay, and if I do that now, I have navigate arrow. Okay. So this is what we did. We should do this inside the source directory so that the paths work. And now load the data. Okay, by now this should be familiar, where we load the data, we get the frequency, so we compute the genes that are between 20 and 80%, and then here we were computing their co-occurrence. It's a bit slow. We should think about cluster this. It's not important. Not important. Okay, and then we had said we were going to be looking at this region here. Six, 77, 78, 79, 80. So about, let's say, and then we imported the arrow ontology, and then if you remember last week we actually ran into some issues related to the import of arrow with some formats, and we had to use the oboe version or not the owl version. And actually in the meanwhile, because of this stream, I think Martin, who's the author of Pronto, he's been fixing things both on his own library, and also actually I think he's been making contributions to arrow as well, so that's actually really great. As I said, I mean, anything that Martin does, you can more or less trust. So then, before just see if we had drawn to. So yeah, so there was some. Yeah, some. Yeah, so he's been making contributions here, right? Alright, so we had done this, and then we had seen these efflux pumps, and this is where we had stopped last week. So efflux. Okay, now today let's start by let's redoing it the same, but let's use the ARG. Oh, CS, okay. I messed this up. I messed this up by renaming CS, reusing the name. Okay, there's two important things that are going to change here. So one is, okay, this is wrong, it should really not be. Did I skip this? I'm just gonna. So there's two things that are gonna change. So one is obviously the plot will look different. This is why I think I skipped rerunning something there. And therefore we should look at the different area of the. Let's look at the different area, and then at some point we'll have to make this a bit more formal. Some point. So we're doing about an hour a week of looking at data, so it's going very slowly. Normally I'd be looking. If this was more of a full-time project, I'd look. This would go over a couple of days, where we'd spend several hours looking, just sort of navigating around the data. Here we're doing it very slowly, or very slowly, in wall clock time. So not particularly slowly in real life or in total time. Just that 1 hour a week is only 1 hour a week. Okay, but so here let's look at this big cluster on top. But cluster on top, so about 0 to let's say this is 45. Okay. The problem here is that this is not going to work at all, because it actually did work for 1 out of 45. But the problem is that many of the other ones, so this is not something that's in arrow BPEF. So for that we are going to need to use argnorm. So how? Actually argnorm is something that you normally use on the command line. I'm just getting rid of. So argnorm, here I have it. Something that you normally use on the command line. I'm just going to open it, and you give it a file. So here. You give it so there's a tutorial, and you give it a file here like this. You say, this is what the input is, and it will output the translated version. So here we're going to be trying to do it. We're going to try to do something a little bit different, or actually very different, which is, we're going to try to use it as a Python library. And this is actually something that in principle the code should support, except we haven't ever really documented how to do it. So this is actually on our to-do list. We will, because what I'm going to be doing now is actually usage that I think would be potentially interesting for others, which is, okay, I should be able to somehow import. Okay, right. Step one, that worked well. So I think I've said this from the very beginning, but one of the motivations for doing extremely open science is also to dog food our own tools. So argnorm is one of our tools. So let's see if we can get argnorm to work. So what I would like to do now is, okay, so I have G here, this name BPEF, and I would like to somehow get argnorm to tell me what G is in the arrow ontology. So G BPEF, this is a gene, or a gene class. I mean, gene is one of these awful words in biology, because the meaning, you can use it, what it refers to is not always very clear. I know a lot of biologists or people who get a bit upset when popular science, when you hear, so and so has the gene for red hair, and people get very upset because it's not a single gene, and if anything they should be saying allele and not gene, but actually we're probably as bad as that, because we also use the word gene to mean several different concepts that are related but not exactly the same. So BPEF is a gene, so it's a family of sequences, and this probably there will be an arrow term that corresponds to BPEF, and what argnorm does, it should let us, no, it doesn't do plot ontology at all, but it should let us transform one into the other. However, having said that, as I said, we don't actually have this is normally used as a command line tool and not in this way. But I always thought it would be a good idea to support the normalizers. Okay, why can't I import normalizers? Let me spell normalizers. Okay, I feel I'm going a little bit. Okay, I feel I did. Okay, I messed this up somehow. Yes, I wanted. Okay, let's import our normalizers, and then our normalizer. Okay. Okay, so there's a deep ARG normalizer, and I'm gonna interchangeably say deep ARG and deep ARG. I actually not sure what is the preferred term. Okay, and then so this is a base normalizer. Okay, base normalizer is this. Okay, that's what I want. Norm. I feel the interface there should be an interface where I can normalize a single or a small set of types, and it should really not be like this. Okay, right. So argnorm, we haven't actually it's still work in progress software. It's beta software. We're trying to get it up to scratch, and this So, and you know, me being here and struggling with it is also part of that. Part of that, because this is how now I'm running into the same sorts of issues that a naive user would, and so I think I'll learn a little bit here as well. So okay, all right. So okay, so actually, I'm gonna take a note of that. Take a note of this future warnings. Alright, so I'm taking. Okay. Okay, right, so this does not look like that. Okay, alright, this also the okay, so maybe this G is BPEF. I'm gonna switch over to R norm again, and I think we have some examples here. Okay, I see. Right, so we have here some examples. This actually I can recognize that this is coming from the GMGC, the Global Microbial Gene Catalog. I recognize the gene ID, and so so here we have ARG van U. Then make some query start. Make this bigger, and then query read ID, and then here this predicted so okay, so here, so this is the output, and it includes so this is probably a specific gene, and there's more than one. Just to test this theory. No, so I was going to say, so this is the gene ID, and it comes from this thing, and here's the gene ID, and here's also the gene ID. But is this a one-to-one? So for van U it seems it is, but I don't want to do this for all of them. I want to do this for all of them. Okay, then okay, alright, so just exploring these things. So there's alright, so the deep biology IDs, so you have some, probably this is some sequence identifier, some internal code features, then one gene identifier, then some, I guess this is a gene class, this is beta or antibiotic class, beta lactam, and then here, so this is some sort of gene, so this is gene and gene family, something, or gene group. I was saying gene is a bad word, but gene family is also just slightly worse. I mean, in principle, and often we use it to mean a group of sequences with a shared ancestry, so some sort of homology, but we're still very undefined what that means, and I've seen people use the term family to mean things that are conceptually or functionally related, even if they do not have a shared ancestry. So again, we are also not very good at, when I say, we as a community are also not very good at being precise in our use of language. I don't know who said that, in every science there's a word at the very center that that nobody really, whose definition nobody really wants you to look too deeply into, and I guess for us that word is the word gene. Nobody really wants to look too deep into what gene is or what's a species. So often these very central terms are very difficult to define. All right. Okay. Enough of this. Let's try to make progress. Okay. All right. So all is not lost, or nothing is lost, in fact. So we have this. Okay, so So I'm just trying to see, if these things are Okay, so I was just trying to see. Okay, so this is I take the index, then use the now this is using pandas because argnorm uses pandas internally, and and so here we're using pandas, and frankly I'm a little bit more in my comfort zone. So I just wanted to check. Okay, so we have we had terms that look like this, and then it seemed that we had terms that look like this as well, and it seemed that maybe one of these was the right match. And so I was just trying to check. So if I take this, then I split it by the pipe symbol. What's that? Oh, okay. And then, so if you're not familiar with this is pandas. So that this string doesn't actually do anything, but it just lets you then call a string type function. So I do a string type function to split, and then I do a string type thing, which is to index. So this is not really a string type function, I guess. It's, but then I do a string type function to convert to uppercase, and now I can check whether. Then I'm going to turn this into a set, just to allow this operation, which is, so I have the set of things that I'm interested in, I have this other set of things, and I'm doing one minus the other, and that's the empty set. So this tells me that there's nothing on this side that is not also on that side. Okay, so this means that I can take this, and I'm actually gonna I'm gonna load it again, so it's not the index, it's just this original index. Okay, and it's not unique. It's a little bit difficult. It's not unique. Actually, it's a good. Okay, so here's a good question. It's not unique, but is. So what do I call it? Gene family. Okay. What are the numbers? is again, I'm going on a tangent, but what I want to do here is I want to check if the families map to unique arrows. What do I want to do? Okay, and I guess okay, let's do this. I'm even more chaos monkey than usual, but sort of okay. So now in this case, so there's one. No, what do I want to do? No, this is not what I want to do. Okay, let's do this. Okay, alright, alright, perfect. So, okay, so Oxa corresponds to 200. Alright, and that actually makes a lot of sense because Ox and Tem, yeah, right, this should not, I mean, yeah, exactly, because by the time we're calling it Tem, we've lost a lot of information because Tem is quite a large family, and so we have Tem 29 and all of the other Tems. Of course, we've lost. They should get their own arrow numbers. And same for Oxa. And these are very important families, and very important also even clinically, very important, very widely studied. So of course they should correspond to many different arrows, because that's really is okay. It really is. Okay, so let's see. Okay, yeah, so we have Oxa as okay, obviously that really shouldn't be the case. It shouldn't be the case that we have. Oh, look how, and they're all ordered. Yeah, this is more or less what you'd expect. Okay, so so what have we learned so far? So we've learned that we've learned that ArgNorm doesn't have the best interface right now for what we want to do. Maybe this means that ArgNorm needs a better interface. With interface, Python API. As I said, we had it's so far been mostly developed as being about the command line interface, command line usage. Here we've thought about this before, that it would be potentially there could be other people who would want to use it as I'm trying to use it now, which is inside some Python script. Get these normalizations, and it would be, it would make perfect sense for us to support that. We just didn't think about it before. So alright, so that's one thing. That's the other thing, maybe a little bit more interesting, is that we've learned that here the tables we have for deep ARG, we're using these broader families and not individual genes again. Noting that the word gene is very, very, very difficult. But yeah, so we have, okay. So what if we, instead of gene families and gene ID or gene name? So okay, this looks much. Okay, so alright, so we have some. Alright, so we still have some of this happening. Okay, I mean stuff like beta-lactamase. Okay, obviously that's going to correspond to. But CTXM, okay, it still makes sense. CTXM is still makes sense that I mean, okay, some of these still make sense that there are multiple mappings. Although OXO1, I'm just out of curiosity. Let's just look at OXO1. Okay, OXO 320. Okay, I'm really not well informed enough to know whether it makes sense that 320 and 1 get assigned to the same name. Okay, yeah. Apparently, OXA 320 is OXA 1 like beta lactamase, so maybe it makes sense. Maybe it makes sense. Just out of curiosity, let's check if OXA 1 is a OXA 1 like. No. Yeah, okay. OXA 1 is also a OXA 1 like beta lactamase. Alright. Which is a oxybeta-lactamase, which is a class D beta-lactamase. I mean, this is why we're such big fans of Arrow, and we're basically piggybacking on all of their work, because it's, you have so much more information here than you have so much more information here where you can distinguish the individual variants if you want, OXA 1 versus OXA 320, and then you can group them into broader and broader classes. So OXA 1 like, which to be honest, I didn't know was a class that exists, and then this OXA and class D beta lactamases, and then these broader groups where antibiotic inactivation enzyme. Although that is also informative, because you can distinguish that from, say, efflux pump. That's actually so. An efflux pump will just, as the name say, pump out the antibiotic, whereas the antibiotic inactivation enzyme will actively destroy the molecule, and this means that there are different strategies to overcome each one. So we know, for example, beta lactamases, there are now anti-beta lactamase or molecules, so beta lactamase inhibitors. And as far as I know, bacteria have not developed anti-beta lactamases, so beta lactamase inhibitor inactivators. All right. Okay. So. All right. So did we make any progress? No. We learned things. So we learned things. We learned things about. I learned things about ArgNorm. Still figuring out. We'll. Still figuring out what to do with this, though. So, for example, because now what we have is this. I'm gonna clean up the code a bit. Cleaning up the code a bit. Okay. Okay, and what I said is that I wanted is to look at the first 45. I don't know what cluster. Let's do. Okay, this is the top. Okay, so alright, just so everybody, so this is this top corner here, and so what we first see is this Van T gene in Van G cluster, Tet A. Okay. Alright, so I mean we haven't. I'm gonna say that this should. Well, this doesn't mean anything, but I'm gonna put a question mark here. So we've been looking at a completely different project, and without going into details about that other one, we often see a lot of vancomycin resistant genes, and that are reported where we really don't believe in them. So there, because if we then look at the alignments, we don't. They're not convincing. So I'm not sure exactly what it is, but in another project we actually we think that there are probably some other proteins that are relatively common that share homology, or so they are homologous to the Van proteins in the Van cluster, in the vancomycin resistance cluster, but the alignments are so they're not great, and so we think that they're good enough that there is homology there, in the sense that what we're seeing are sequences that are evolutionarily they share an ancestor with the vancomycin resistance, but they are not similar enough that we're comfortable with the functional assignment, right? In the sense that they probably do something different, something that's probably related-ish, but not vancomycin resistance. And so one of the projects I've had, because I've been sort of not systematically, but collecting some of these observations, and actually I would not mind if to work a bit, but this would not be more than just a bit. This would have to be someone's project for maybe a year or longer to do a antibiotic resistance classifier that was very, 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 very much aware of these things. Because one of the other things why we think there's a lot of vancomycin is because there's some. Often we'll see one of these. So we'll see in the genome, be it the MAG, whatever. We'll see one of these, peaks of there's this one Van gene, but it's just one so the other ones are missing, the alignments are poor, and so we really don't trust that. Tet A60, I'm not sure about these other ones. But just to develop a little bit more intuition, let's do this is what I wanted to do. Okay, so this is okay, we're going over time today. All right. Okay, so when t that a. Okay, alright, efflux pump. Colistin resistance. Okay, alright, penicillin binding protein mutations conferring resistance to. Okay, this is a mutation. Mutations are always again. They are. We'd have to be a bit more careful and look at the alignment. So this. It's not that these things don't exist. They exist. In fact, they are very, very serious. But often our tools are not great at detecting them. Okay, again, a lot of efflux pumps. Okay, all right, but I think I'm quite happy that we've made some progress today. We have. We learned. So I'm gonna wrap up again. I'm gonna clean up this code, just this exploration of Oxa or whatever this thing. Just clean up. Okay, so this is still pretty much exploration code. So I would not be saving this. So I'm gonna switch back to the log. Yes. So what I'm gonna do is I'm gonna do this. Okay. Yeah. So I'm gonna move the. So I moved it away to 2, and then switched back to the log, and then I moved it back. And just out of habit, move -I just to get that confirmation that yes, we do want to overwrite it, even if. Okay. In this case, yeah. So. This case, this is still nowhere near code that I would be happy to commit, because this is it's all sorts of copy and paste, like this here, like to this, so generally I would I would just keep it uncommitted and keep working on it, and eventually do a little bit more, but since we are out of time, I'm going to okay. Oh, and the other thing, and this is actually kind of important. Did we put argon here already? Let's put argon here. Yeah, we actually, probably we will be making some changes to argnorm, or at least maybe not we here on the stream, but I'm taking some notes here, and I'll be communicating them to Vedant as well, who's now the main person who's responsible for argnorm. And yeah, so some of what we do here on the stream will influence how an argnorm works. Particularly, as I said, we have this idea that argnorm should be usable as a Python library. This was not something that we had thought about too much at the beginning. We were really just thinking, we should just have a tool. And actually, to be honest, at the beginning it was something I was thinking about it as internal, because we had these projects about looking at antibiotic resistance, and we thought, oh yeah, this would be nice to have a tool like argnorm. Doesn't exist, so let's just do something for ourselves internally, and then we put it on GitHub. We were using it internally, and then at some point we realized that there were other people using it on GitHub, and I also realized that when I talk about it, when I do presentations, when I do presentations, argnorm was something that would show up, or in a question. So I present, and argnorm would be there. We have maybe 30 slides, and argnorm would be half a slide. So part of this antibiotic resistance, and then there'll be, and then at the end, people would ask, oh yeah, what about this thing about comparing args across tools? We've been doing the same. So I started to realize that it was actually very useful for others, not just ourselves. So now we're trying to go back and retrofit argnorm into retrofit argnorm to make it from just something that was useful internally, that in some ways worked really well for us, but was not into something that we can use as a tool. I'm seeing the chat. Yeah, looking some alignments for QC. Yeah, maybe I can show some of these in the future. So I was a little bit vague because I'm not sure what I should be. I'm pretty happy to talk about my stuff that's just mine. But sometimes if it involves other people, I'm not sure how much they want me to show off their stuff. But we can maybe look at some of these in the future. For sure, I'll try to find something a little bit without a lot of context that would be that would be not mine to share. But yeah, we can see some of these things. I mean, sometimes it's a little bit difficult. So you're making a judgment call, but sometimes it's pretty obvious if if you have just a low identity, so the problem is, if you have a low identity match, a low identity, let's say 50% amino acid level, this is real biology in the sense that you really have two sequences that are related, so they will share a common ancestor. You do not get two sequences being 50% identical by chance. That's just the probabilities are just infinitesimal basically, and so you can definitely conclude that there's shared homology here. So that is a valid conclusion. The next conclusion would be, okay, therefore they have the same function, and that is where I think it's a little bit iffy, because a function is another of these words that we have no idea what it means. Probably they do have the same function in some very abstract sense, so if you have but they will probably have very different they'll probably have very, for example, they might they might both be proteases, they might both cleave proteins, and so in that sense they will be the same function, but then they will be already so different that they will not have the same targets. So I think this this is, so we have these tools like, you know, BLAST and the BLAST derivatives like Diamond and MM62 and whatever else that finds these homologs, but then to conclude, oh, therefore they have the same function, and to say that in the sense that if one is an is an antibiotic inactivator enzyme, the other one is also an antibiotic enzyme. That's the jump that I think is a little bit iffy, and sometimes we will know that we can know that this is not true because we will see that there are other, for example, the efflux pumps. We know that there probably is an efflux pump, but whether it's really pumping out this antibiotic, probably not. Because sometimes we will know that, oh yeah, there's a variant that's very similar, or more similar, that's been characterized as pumping out something else. So I think as I said, it's not there's still a judgment call there, but often there are also bad incentives for tool developers, in the sense that people like tools that report a lot of results. So people like tools that report that they found 1,000 antibiotic resistant genes, much more than tools that say we found 3, because I'm not confident about the other 997. This is a major issue, and that we've always want more. A tool that finds more is seen as better, for better or for worse. All right, so let me just push out. I do want to. Okay, we'll have to figure. Okay, pushing this. Push. Oh yeah. I'm gonna push the log branch. So should I play the outro music? Yes. Let's see. Let's play that. Yep. And okay, so I was so this week I'll do a quick recap. I'll do the recap including both weeks. And I'll have a lot more time going forward. At least not this crunch time last week. So I hope to see you then. Otherwise, I'll see you on the Discord or on the mailing list. All right.